Hello, everyone. Thanks for joining. Thanks for the introduction. I'm Panagiotis, and this presentation is about the new cooperative task execution framework for Apache Spark. This is joint work with Konstantinos and my supervisor, Peter Pichuk, at Imperial College, London. This work actually started with an observation that analytics frameworks such as Apache Hadoop, Storm, Heron, and Hive were traditionally dedicated to either batch or stream processing. Eventually, they started converging, unifying stream and batch use cases by exposing different APIs. For example, remember how the dstreams API evolved on top of the traditional RDD API to enable stream processing for Apache Spark. However, to implement your stream and batch jobs, you would have to implement them as separate applications. Only recently, these analytics frameworks started exposing unified programming interfaces to seamlessly express stream and batch as part of the same application. Also, remember what happened in the keynote speech here today about the Delta Lake. In Delta Lake, they tried to unify stream and batch processing. So Spark Status Streaming and Flink Table API and now Data Lake provide such programming interfaces, enabling users to actually develop both stream and batch processing as unified applications. So let me start by giving you an example of a unified application motivated by a production workload. This application implements a real-time malicious behavior detection service consisting of a training job using historical data to train a machine learning model and an inference job performing latency-sensitive inference to detect malicious behavior. To do this malicious behavior detection, it's also using the model which is previously trained. And using the unified application design, we can actually share this state in memory. So this is just one of the advantages of using unified applications, sharing state. Other advantages include sharing of application logic, better application management, consistent results between streaming and batch versions of the same job, and also enables jobs to even share computation in the future. So such unified applications are known with different names. They are known with names such as continuous applications, complex applications, unified applications. But what they all essentially do is they actually combine latency-sensitive jobs with latency-tolerant jobs as part of the same applications. And for the rest of the presentation, I'm going to refer to those unified applications as stream batch, with stream being the latency-sensitive part and batch being the latency-tolerant part. So Spark added support for those unified applications using with the structured streaming API. And in case you are not familiar with that API, it is essentially a unified processing platform built on top of the Spark SQL engine, on the SQL APIs. It is, of course, fast, scalable, and fault-tolerant. And it provides a large ecosystem of data sources that users can actually read data and write data. It also provides rich unified high-level APIs in the form of data frames and data sets, enabling users to deal with complex workloads and complex data. So if we wanted to implement an application, similar to our example, in structured streaming, we would probably use the same API, as you can see here, very same straightforward API, to implement a batch job, as you can see on the left, performing model training by iterating over some historical data and training the pipeline model you can see here. And we would also implement something like a stream model, as you can see on the right, computing a series of aggregations on some real-time Kafka input, and using the previously trained model to detect some malicious behavior. However, even if it seems straightforward, and despite the fact that these application support from the API point of view is there is very little done at the scheduling side, capturing and satisfying the diverse job requirements of those applications. For example, in the motivating example I just showed you, we probably want to have the minimum delay for the inference job. So we want to execute the inference job with the least latency possible. And at the same time, we wouldn't want to compromise in terms of throughput for the batch job. And we want to do that in the most efficient manner. So we don't want to just throw extra resources to our application. We want to achieve the most out of our existing resources. So in the most efficient manner, of course. So the challenge here, and the focus of this presentation, the focus of this work, is how to schedule unified application jobs while meeting their diverse requirements. So let's see, how would we schedule such an application, such a unified application in Spark today? The application code, similar to the code I showed you before, would be submitted to the Spark driver using something like Spark submit. And the driver, using the same context, will run application jobs through the DAG scheduler. The DAG scheduler would split its job into stages. And as you can see here, we have 2 jobs, the inference job and the training job. And then we have dashed rectangles representing those stages. So for example, we have 2 stages for each job here. Every stage consists of some tasks running some computation, taking some time t. Some tasks are more computation intensive than others, taking longer. For example, you can see that stage 1 tasks of the training job take longer, they take 3t instead, because they're more computation intensive. And actually, the number of tasks of each stage is defined by the number of partition the stage operates on. So namely, stage 1 and 2 of, what's going on? Yeah, stage 1 and 2 of the inference job operate on 2 partitions, while stage 1 of the training job operates on 4 partitions. So if we want to run those jobs or run those tasks and actually satisfy the requirements, how would we do that? A typical straightforward approach is actually implement those jobs as different applications and run them using static resource allocation. In static resource allocation, we could actually dedicate some specific amount of resources to each job. So let's assume we have 2 executors here. We have executor 1 and executor 2. Executor 1 uses 3/4 of the available resources. Executor 2 uses 1/4 of the available resources. And then we will schedule each job on its executor. So let's say that the training job is more computation intensive, so it's going to run on executor 1. So we would schedule each stage of each job using the available resources until these tasks and this stage is actually complete. As you can see, in this scenario, in static allocation, even though the stream job latency is low, it's still 2 times higher than the optimal. And more importantly, we end up with a bunch of wasted resources. As in static allocation, there is no way to share resources across jobs. And this is the main drawback of this approach. A more resource-efficient solution would be to actually use the Spark structure streaming, where we have the unified engine sharing executors. And then we would actually implement both those jobs as part of the same unified application, right? So by default, Spark structure streaming schedules jobs using FIFO scheduling policy, where the first job runs to completion. Assuming that this is a training job that is submitted first, it will use all available resources, and then it will run until completion, and then the inference stages will be scheduled. However, as you can actually see, FIFO causes significant queuing delays, and it has even more latency than the static allocation. So the main drawback here is that the stream job latency is increased, mainly caused by long batch jobs that cause extra queuing. So an alternative here is to use FAIR. FAIR is actually scheduling policy equally sharing resources across jobs. And this could also be a weighted share. And under FAIR, we would first schedule 2 tasks from each job stage, and then the next equal share until completion. FAIR successfully manages to reduce the stream job latency by 2t compared to FIFO, but as you can see here, we still have some queuing. And this is a fundamental problem, as we cannot guarantee optimal latency for the stream jobs in FAIR. We cannot avoid queuing. We still have the very same problem, even though we are more resource efficient. So you can see the packing is a bit better, but still there is queuing, leading to increased latency of our latency-sensitive jobs. So how would we actually avoid queuing completely? To avoid queuing completely, it is possible to use something like non-work preserving preemption. So killing, for example, tasks whenever we need to run something that is higher priority. So in that scenario, we would probably couple a scheduling policy such as FAIR with kill, which is preemption, to satisfy our requirements. So how would we do that? We would schedule tasks in a fair manner, similar to before. And then when high priority tasks need to run, we will probably preempt all running lower priority tasks in favor of those streaming tasks, right? So the problem there is that even though we achieve and we minimize the latency, we have no queuing there, we have to restart all the kill tasks, losing any progress they made thus far. So we end up with a bunch of wasted resources. So with killing, we can actually achieve, and preemption, non-work preserving preemption, we can actually achieve better latency at the expense of extra work, as we have to restart those jobs. So my question here is, since we have those stream and batch jobs, these lower priority and high priority jobs that run as part of the same runtime now, can we actually do better? And this is what we're trying to do with Neptune. In Neptune, we're trying to minimize both queuing and wasted work. And how do we do that? We schedule tasks in a similar fair manner, but whenever we have high priority tasks, we want to suspend the lower priority tasks in favor of our latency critical tasks, and then resume them later on when we have available resources without actually losing any progress. And this is what we're trying to do. Of course, it's simpler to say that than do it, but we have a few challenges to solve here. So first, as I mentioned, how to minimize queuing for latency-sensitive jobs and wasted work. This is our goal, but how do we do that? We also want to natively support stream batch applications. So how to support all those kinds of different unified applications. And finally, how to satisfy different stream batch job application requirements. So these unified applications can consist of different number of jobs, different priorities. How do we support all of them? And at the same time, we also want to achieve high-level objectives. For example, how do we balance the load in the cluster? So Neptune is our new execution framework for stream batch applications that implement suspendable tasks to minimize both queuing and wasted work. It is built on top of Spark structured streaming to provide a unified execution framework for stream batch applications, supporting all those unified applications, and introduces also pluggable scheduling policies. These pluggable scheduling policies can satisfy a variety of stream batch application requirements and also high-level objectives. And they're pluggable, so users can implement their own scheduling policies. So to implement the suspendable task, we first studied how tasks are implemented in Spark today. Tasks are implemented in Spark today as subroutines, which are pretty much applying a computation function on top of a partition of data given as an iterator. And as they're implemented as subroutines, they run in the executor to completion. So to run the executor of this task actually has a call stack, as you can see here on the right. And the executor actually allocates space for the return value of the function in the call stack. It also adds a function reference there. It allocates space for the variables in intermediate state. The problem is, since they're implemented as subroutines, they have to run to completion. So what happens if we have a high priority task that needs to run immediately? What are our options? Our options are actually two. Either we're going to kill this task, making space in the executor stack, and lose any progress made, or we're going to checkpoint the task, leading to unpredictable checkpoint times, because sometimes we don't know how much data we have to checkpoint there. So instead, what we do in Neptune is we use coroutines to implement our computation functions. So in coroutines, we use separate stack to store the variables, and we also add yield points after the processing of each record. And then these coroutine computation functions can cooperate with executors. And this is why we named our framework Cooperative. So now the executor, similar to before, to run a task, will invoke a special call function, which actually creates the coroutine stack instance to store the function reference variables and the state. And when the executor wants to preempt a low priority task in favor of a high priority task, the only thing that needs to do is actually mark the context of this specific task as paused, and then the task will yield in the next record iteration back to the executor. Then the executor can decide to run something that is higher priority or resume this task later on. So this is how we implement cooperative preemption, and we manage to suspend and resume tasks with millisecond latency. At the same time, we preserve work and avoid wasting resources. Of course, I have to mention here that since we implement the computation functions as coroutines, the users don't even have to know how these tasks are implemented. So the users still use the same data frame, data sets, RDD APIs, and since we implement those computation functions under the hood, it's completely transparent to the user. Another thing I have to mention is, since we're using stackful coroutines, we can implement more complex logic. So we can actually compose more complex logic of tasks by coupling a bunch of those coroutines together. So to give you an idea how suspendable tasks are implemented in Neptune, the code snippet on the left shows the implementation of a collect action in Spark today that receives the task context and a record iterator as argument and returns all dataset elements. Of course, these dataset elements can be partitioned across the cluster. And then if we wanted to implement the very same logic, the very same action using coroutines, the only thing we have to do is actually add these two lines in bold there. These two lines actually check if the context of the task is marked as paused, and they yield control back to the executor. Then the executor can actually decide either to run something that is higher priority or resume the task later on, for example. The problem now is that since we don't just assign tasks to executors based on free resources and task locality, we also have to make more scheduling decisions and more involved scheduling decisions. For example, we have to decide when to suspend and resume those suspendable tasks, right? So NEPTUNE, to do that, NEPTUNE actually supports pluggable scheduling policies, deciding when and which tasks to suspend. But let me walk you through an application example and see how this application is executed in NEPTUNE. A user implements the application consisting of a bunch of jobs. And then it's the user's job to actually mark the jobs with specific job priorities. These job priorities can be, for example, low, or as you can see with green, or high with red. Then the user can actually submit this application in an API of Spark. For example, it can submit the structured streaming API, which is using the microbatch model by default. And then the structured streaming engine might decide to incrementalize the plan and optimize the execution plan. This plan is given to the task scheduler, computing the plan of each job, consisting of stages and tasks. You can see the high priority tasks here are with red, the lower priority tasks are with green. Tasks that are ready to execute are then passed to the task scheduler. And then when a new task actually arrives, it is immediately executed. It is immediately going to the running queue in the executor when resources are available. When we don't have resources available, the task scheduler can actually ask the scheduling policy to make the next decision. And what will happen is, in this scenario, for example, where we have a high priority job pending, the task scheduling policy will actually decide to suspend a lower priority task, so put it in the paused queue, and then run the high priority tasks instead. Of course, when we have later on some available resources, this low priority task will continue execution without losing any progress. As you can imagine, there are a few challenges we have to solve there, and it's quite a challenging task, for example, to suspend and make suspension decisions and scheduling decisions fast. One decision we made, for example, is to have the suspend and run task implemented as a single action. So in a single round trip with both suspend and launch the new task. Of course, the scheduling policies also take into account a bunch of different things. For example, they take into account the task priorities, the cluster state, executor priorities, for example, the memory used, and all that kind of stuff. So as you can imagine, the scheduling policy is a quite fundamental part of NEPTUNE. The main idea of those policies is to actually trigger task suspension and resumption, but they have some more specific goals. For example, we want them to guarantee that stream tasks can always bypass lower priority batch tasks. And we also want them to satisfy high-level objectives. Such a high-level objective is balancing cluster load, for example. At the same time, we don't want to suspend always the same task over and over and over again and avoid making any progress. So we want to avoid starvation. The way we avoid starvation is by simply setting a limit on the number of times we suspend a task. After that time, this task is going to run until completion. And this is how we make sure we always make progress. Currently, in NEPTUNE, we implemented two very simple scheduling policies that seem to work quite well. The first scheduling policy is called the load balance scheduling policy, equalizing the number of tasks per node and reducing preemption. And for other jobs that task locality and data locality is more important, we also implement the cache-aware load balancing, where we respect task locality preferences in addition to load balancing. We implemented NEPTUNE on top of Spark 2.4.0, and we're going to open source this code. And as you can imagine, we had to port all the computation functions, so all the result tasks and shuffle task functionality across programming interfaces to use coroutines. So we had to implement all the RDD data frame and dataset APIs to use coroutines instead. We also had to extend the DAG scheduler to allow job stages with different requirements expressed as priorities. So these job priorities are actually hints given to the scheduling policy to make the right decision, which task to preempt and when. So now let me show you how to actually use NEPTUNE to run very simple unified applications. So what I'm going to show you is how to run two jobs, part of the same unified application, a high priority latency sensitive job and a low priority latency tolerant job. And we're going to schedule them using default Spark and NEPTUNE. And what I wanted to show you is how easy it is to use actually NEPTUNE. We actually have to just add an extra flag, so the priority flag there, and mark the job as low or high priority. And we're still going to use the very same API of Spark. So let me go into that. So let's see what we have here. Okay. So we have our application defined here. In IntelliJ, we have
a multi-job consisting of 3 jobs. The first job is actually a very dummy warm-up JVM job. And then we have, oh, sorry. Yeah. So I probably have to mirror the displays. I guess. Yeah. Better now? Yeah. OK, so let's go through this example. We have a multi-job switch, pretty much a unified application using the RDD API, but you could do the very same thing with any API, actually. So this unified application consists of 3 jobs. We have a very simple dummy warm-up JVM job, and then we have 2 aggregation jobs. So the first is a low-priority job, as you can see here, aggregating 100 million elements, and we actually measure how long this job takes to run, and then we submit it in a separate thread. And then after half a second, we have a high-priority job that we want to submit. We're going to use just a single core here just to show you what we're trying to achieve here. But you can do the same thing with any more complex logic, right? So we have a high-priority job here aggregating less elements, so just 1 million of elements. And we also measure the time it took. So ideally, what we want to do is actually have the high-priority job run as fast as possible, and then the low-priority job consume the rest of the resources. But since the low-priority job is submitted first, it's going to add queuing to the latency of our stream job. So even though our stream job only took a few milliseconds of computation, it still took almost 5 seconds to run, as you can see here. So let me show you in the UI what actually happened. So we have the warm-up JVM job here, which we don't care about. And then we also have the low priority job here. And as you can see, the runtime of this job was 5 seconds. Then if we go to the high priority job, which is the next job actually, and we check the timeline, we can see that most of this time was actually queuing. You can see that it was queued for 4.5 seconds, and the computation was only 50 milliseconds. So you can see that we have some extra metrics we added in the timeline here. We have the queuing latency, the pause time, and the runtime. And my question is, can we actually do better? Can we avoid these queuing delays that we have here that are in the order of seconds? And we can actually do that using NEPTUNE. So in NEPTUNE, we have the exact same code as before. As you can see here, it's exactly the same code. We start from here, and then we have the warm-up job, and then the low-priority job aggregating 100 million elements, and then the other job aggregating 1 million elements. The only difference is we just enabled coroutines here, so this is just a flag what we enabled, and we also marked the local property of NEPTUNE priority. So NEPTUNE priority is actually the extra hint we give to the task scheduling policy, to NEPTUNE scheduling policy to make this preemption and suspension, right? So NEPTUNE priority of 1 means it's higher priority than NEPTUNE priority of 2. So this is how we mark the low priority job and the high priority job. So if we run the very same example now, what we will see happening is actually the high priority task will suspend the low priority task and will finish in a few milliseconds. And then, as you can see here, and the low priority task will still run and will be resumed later on, running for 5 seconds in total. And if we check the UI, what actually happened, this is the high priority task. As you can see here, what happened is the queuing latency was reduced to a few milliseconds, like 15 milliseconds, and the runtime was 70 milliseconds. So we did what we had in mind. We reduced the queuing latency to minimum. And then if we check the low priority task, what happened in the timeline there, we have some suspension points here, and these suspension points are marked with red. So this task specifically was suspended for 78 milliseconds, and then it was resumed later on without losing any progress. So this is what we achieved with NEPTUNE. To make things a bit more interesting, you can implement any complex logic here, but to make things a bit more interesting, I'm just going to add a few iterations here. So let's assume that we have more low priority jobs that are submitted, and we have the longer job that is going to be suspended for more than once, right? So let's see how NEPTUNE does that. What will happen here is we're going to submit 5 low priority tasks, 5 high priority tasks that finish after half a second. And then what will happen here is the low priority task was suspended for 5 times, as you can see here, and managed to react in a few milliseconds. So this is what we achieved with our suspendable tasks and our scheduling policies. So that's what I wanted to show you here. The takeaway was actually you have to enable just a flag, and also the API is exactly the same, and you just mark the job priorities using this local property. And this is how you use NEPTUNE out of the box. So let me go back to the presentation now. Okay, so that was that. And for the evaluation, we actually used different workloads to see how NEPTUNE behaves. So we have TPC8, a decision support benchmark, we have Yahoo streaming benchmark, and we have LDA. LDA is pretty much a machine learning training inference application, similar to our example, where we have a unified application consisting of inference and training as part of the same app. And then we run those benchmarks, we run those workloads in an Azure cluster consisting of up to 75 nodes with 4 cores and 32 gigabytes of memory each. So first, what we want to see is actually compare NEPTUNE with existing approaches and see how it does in terms of stream latency. We want to minimize the stream latency, so how close we are to achieving our goal. So what we did here, we used the LDA application, so similar to our motivating example, with a latency-sensitive inference job and a latency-tolerant training job, and we first ran the stream job, the inference job, in total isolation. This is just to get an idea what is the optimal latency we can achieve. As you can see here, running the inference job in a total isolation is close to 1 second for the 99th percentile. We then run the whole unified application consisting of both inference and training using structured streaming, so using default Spark with FIFO and FAIR scheduling policies. So we observe that using FAIR actually reduces the 99th percentile by 37% compared to FIFO, but is still 2 times higher than running the job in isolation. So a way to avoid queuing, because we believe that queuing is actually the reason for having the extra latency there. So a way to reduce this queuing is actually implement a preemption on top of FAIR. And this is what we did there. So by adding preemption to FAIR, we managed to reduce the median runtime, the median latency by 54%. But as you can see, though, the 99th percentile is still high. And the reason for that is we cannot preempt using FAIR and preemption. We cannot preempt more than our weighted FAIR of resources. Then we run the whole unified LDA application using NEPTUNE and our 2 different scheduling policies. So we have CLB, which is our cast load balance scheduling policy, and we also have LB, which is our load balancing policy. And as you can see, we have quite tight distributions, and they're quite close to the running the job in total isolation. As you can see, CLB, cast load balance scheduling policy, achieves 99th percentile just 13% higher than running the job in total isolation. And LB achieves 99th percentile latency just 61% higher than running the job in total isolation. And this is actually pretty good, and actually tells us that this specific job also has some data locality that needs to be respected. That's why CLB performs a bit better. Just for completeness, we also run those jobs as separate applications as in the motivation. We run them using static allocation, where we use different executors for each application. And as you can see here, even though we have quite tight distribution in terms of latency, the 99th percentile is quite high. And this is actually caused because of executor interference. So we have executors, different executors on the same machine, competing for the same resources, and this is actually increasing the tail latency. So the key takeaway here is with NEPTUNE, we actually achieve latencies comparable to the ideal for the latency-sensitive job, which was one of the first goals we wanted to achieve. So next, we wanted to measure the effectiveness of our suspension mechanism. So to do that, we use the smaller cluster of 4 nodes, and we run TPC8 with scale factor of 10. And as you can see, the x-axis shows the 22 different queries of the TPC8 benchmark. The y-axis shows the latency there. And what we did first is we actually ran TPC8, and we measure the task runtime distribution for each query, which ranges from hundreds of milliseconds to tens of seconds. What we did next is we rerun the benchmark by implementing the custom task listener. This custom task listener was continuously transitioning tasks from running to pause state and from pause to resume state until they complete. And as you can see here, the red box plots and the blue box plots show the latency distribution of those actions. And as you can see, we managed to effectively pause and resume those tasks with sub-millisecond latencies, although the queries follow this different runtime distribution, which is showing the effectiveness of our mechanism. So as some applications actually require more resources than others, we also wanted to experiment with the impact of resource demands in performance. So to do that, we took the Yahoo streaming benchmark with two different instances. So we took a latency-sensitive instance and a latency-tolerant instance as part of the same unified application. And what we did is, while the batch instance was using, so the latency-tolerant instance was using all the available resources, we increased the resources used for the streaming instance. And we measured the streaming latency, as you can see, on the y-axis. So first, we measured the latency, and Neptune managed to maintain low latency across all percentages, even though the tasks that had to be suspended increased. This is actually showing, again, the effectiveness of our preemption mechanism. But since we're preempting more tasks, more and more tasks, for example, for the 100%, we had to suspend the whole cluster to run our high-priority tasks. Since we suspend more and more tasks, we expect the batch tasks to take a hit in the throughput. And this is actually true. As this batch task preempted increase, they take a hit in the throughput, which in this case, however, is below 2%. And what this shows is actually we managed to efficiently share resources with low impact in throughput using Neptune. What I also like about this figure, it's also like a glimpse from the past to the future, with 0% being the static allocation case, where we have different executors and different resources for each job, depending on the requirements, and 100% being a share everything approach, where we have all the jobs running as part of the same runtime, the same executors. So to sum up, I presented Neptune, which is a new task cooperative execution framework supporting complex unified applications with diverse job requirements. It implements suspendable tasks using coroutines and introduces pluggable scheduling policies. As the next step, we also believe that it's going to be super useful to integrate with the continuous mode of structured streaming, which we believe is the future, and also the Delta Lake is a step towards that as well, right? So with that, I would like to conclude, and I will be happy to take any questions.
Hey guys, if you have any questions, please step up to the mic so that everybody can hear you. Just kind of make your way over to the middle and ask them if you can.
Hey, great talk. I suppose priority is determined by users, and my questions are, do you have any insights? So if there's one high priority job and 10 low priority job, then this will obviously work well. But if all the jobs are high priority, then they are not useful in guiding the priority anymore. There's this priority inflation. Do you have some insights into like what percentage of the workload can have high priority before this lacks the usefulness?
Yeah, good question. Currently, we have only experimented with low and high priorities, but what you're saying makes sense. My intuition is that if the high priority tasks consume at most all the available resources, so even if you have more than one high priority jobs, if there are enough free resources to accommodate all the high priority jobs, it should be fine. And depending on the scheduling policy and decisions, for example, you would always suspend the low priority tasks in favor of your high priority tasks, but you could also implement something more complex there. But imagine that even if you have more high priority tasks and you have available resources to suspend or run, then you should be fine, even if you have more than one high priority job. Does it make sense?
Kind of along the same lines. Hey, thanks, by the way. Great talk. Along the same lines, I'm presuming that this coroutine stack is in memory somewhere. Mm-hmm. So could you speak to the implications about that? Maybe two particular things. One is I'm presuming I'm going to need a lot of extra memory available because I'm suspending jobs. And then two, what happens in case of a crash of the cluster? Is it persisted? What happens when it comes back? Thanks.
Yeah, good question. There are a few things there that I didn't dive deep into. So one thing is all the workloads we experimented with were not memory bound. And what we see in production clusters is actually memory is not usually a problem in most of these workloads. In the case that memory is an issue, you have different options there. So one thing that we're currently exploring is extending our scheduling policies to take into account, for example, the memory pressure of the executors. Right? So when your executors run low in memory or they have increased garbage collection times, your scheduling policy or preemption policy could be less aggressive there. In practice, in production clusters, we didn't find that memory is an issue for most of the workloads we run. In case you have that, you have options. Either reduce the tasks that you preempt, so preempt less aggressively, or make your scheduling policy smarter, taking this into account. So regarding the fault tolerance, since we're operating on task level, we can still use lineage to re-execute whatever failed, right? So we don't expect it to be an issue in that case. But in general, the concept in NEPTUNE is keep things in memory because you want them to be low latency. So this is the motivation for us. Of course, we could checkpoint them. Of course, we could do a bunch of things there, but we want to achieve the best latency possible for our latency critical tasks.
So the question I had was about auto-scaling, right? So in the case of preemption, right, more tasks are getting executed with the available executors, right? In an ideal scenario, the tasks that are waiting, they would have led to like fetching of more executors, right? So you're kind of like becoming in the way of auto-scaling. So how do you guys factor in auto-scaling coming into effect?
That's a very good, I mean, we haven't looked at auto-scaling, but I would be happy to discuss ways to do that. We can discuss that offline. That would be interesting, actually. We haven't looked at it.
Sure. So the other question was already asked about the memory reasons, right? So in the case of, so this is clearly a very good streaming use case. So is it a good idea to have batch and streaming running in the same sort of application or environment where streaming has a higher priority, where batch keeps getting interrupted? And batch can have like more memory being stored in the executors and so on.
It really depends. It really depends, but I think it's a good, it has a benefit, right? Similar to the advantages I showed you in the first few slides, you have the advantage of sharing state, for example. You have the advantage of sharing resources. You have the advantage of of not writing the same application code again and again and again. But it really depends on the workload. I believe that there will be always cases where you want them to be separate, but in the cases that you can unify and you have the option to do that, you have better and more efficient ways to do that, right? So maybe it's not a good fit for everything, but for some cases, sharing the resources and sharing the executors does make sense because you're more resource efficient, right?
Cool. Thank you.
Hi. It seems like you've implemented cooperative multitasking, and I'm wondering if you have any thoughts about an alternative approach of relying on the operating system's multitasking, perhaps with threads that have different priorities. And one reason why I'm interested in this is I'm thinking of a scenario where a high priority task is blocked on I/O, and so maybe that's an opportunity for a lower priority task to execute.
We're actually exploring currently how to implement that with, as you said, multitasking in the operating system. But what you want to avoid there is usually the third priorities that you give to the operating system are like hints. There is no way to actually guarantee that these will be respected. So if you want to guarantee that, for example, your high priority task will always be high priority and will be always prioritized, you have to do something in the application level. But we're definitely thinking ways to combine such things and then see how it does, or at least compare how would this behave with operating system scheduling. We're currently doing that.
Thanks.
Hi, I think you've touched on this in your presentation, but I was wondering if you can maybe either repeat or drill down a little bit more into how the context of a preempted task is stored and restored back, and how these scenarios work in cases where things don't work very well, like a crash of containers.
Yeah, so what I did show here is actually that all the tasks are pretty much part of a call stack, right? So this is pretty much how you run tasks, or any function pretty much actually, in a programming language, right? Where you allocate space in a call stack. This is the executor call stack, let's say. You have a main, let's say, and you run a function. Then you have to allocate space for the return value, for the function reference, and the intermediate data. And this is what you care about, right? So the problem is, by using subroutines or closures or however tasks are implemented in tasks today, you have to wait for those tasks to finish, right? And then to empty this call stack. And then what we do instead with coroutines, this is actually a feature of coroutines. We didn't reinvent coroutines. It's just getting more attention recently. Coroutines are getting more attention. So the way coroutines are implemented, they have a separate call stack where they store their intermediate state. So what we do is we actually keep all this state in memory, and whenever we need to resume it or suspend it, we can just continue from where we left off, right? So this is what I tried to show you here with context and the yield points. Whenever we yield back to the executor can actually run something else and then take this call stack that is stored separately and then resume it later on. So this is how we checkpoint all the intermediate state and data.
So nothing is spilled on disk or loaded back from it?
No, again, since we're targeting really low latency workloads, similar to what I tried to show you, it doesn't make really sense for us to checkpoint. But we could definitely use something like what is done in Spark today to checkpoint those. But for starters, we just focus on really low latency and we keep everything in memory, since we didn't find any problems in practice.
Yeah, I was just curious, do you do anything to make sure that the low priority tasks don't get starved? Like if just a continuous stream of high priority tasks come, the low priority tasks might not make any progress if they keep getting preempted?
Okay, so you're talking about starvation pretty much, right?
Yep.
Yeah, so this is what I tried to mention here, where I actually mentioned what the scheduling policy goals are, right? So one of the scheduling policies, one of the goals of the scheduling policies is actually avoid starvation. And to do that, we actually have a limit on the number of times we preempt a task. We can say that after we preempted this task, we suspended this task 10 times, don't do that again. Otherwise, we cannot make progress, as we very well said. So I actually found this to be a problem in the beginning, and then I added this very simple policy that seems to work. And yeah, the worst case scenario is your high priority task will wait a bit longer, and then that's it. But you avoid starvation, you avoid dead cases.
Awesome, thank you.
Thank you.
It's a very good presentation.
Thank you.
Hey, so I was wondering, like, by when would this be available in open source? Any date or version that you have targeted?
I'm up for it. So let's take it offline. Let's discuss. And if there is more people that need it and they think that it's cool, I'm up for it. So I'm going to open source it as a separate project anyway. This is part of my PhD, and I will open source it. But if somebody thinks that it should be part of Spark, and there is enough people that think that, I'm just saying, let's talk about it.
Okay. My second question was, how is this dependent on some kind of cluster resource manager, like Yarn or Mesos? Because cluster managers also do something similar, where they look at the resources available in the cluster, and they decide like what to allocate versus what not to allocate.
That's a good question. So when I first started working on this project, we were thinking of different approaches, right? So we have the basic problem of having high priority jobs and low priority jobs. What would you do there? If you go to the scheduler level, there's a lot of things that you can do, but they're in a coarser granularity, right? So what you could do is, for example, take the container, suspend the container, resume it later, stuff like that. There are other research out there that has looked at similar problems. The main problem I see there is it would never be super low latency. So by adding this type of resource management or scheduling decisions inside Spark, which is now a unified engine, you can actually make scheduling decisions much, much faster. And then without relying on the operating system to take its own hints, you can satisfy your goals in a finer way.
Okay, so this is completely independent of whatever resource.
This is on top of Spark. It's on top of the unified engine. It doesn't rely on any resource managers. But what I'm trying to say is that the resource managers operate on a coarser granularity. So it would be really hard to achieve such low latencies as sub-millisecond latencies, no matter how well you do it.
Thanks, really nice presentation.
Thank you.
All right, guys, we'll cut it there. Thanks, Panos, and
Thank you.
great presentation. Thanks, guys.
Thank you.